If you want to understand why one side of the planet is choking on wildfire smoke, while the other is drowning in torrential floods, you don't look up at the clouds, you look down. Specifically, you look at one isolated patch of water in the Pacific Ocean. A temperature shift of just half a degree Celsius in this specific spot triggers a chain reaction of global weather extremes. This recurring climate pattern is called the El Niño Southern Oscillation, or ENSO. It is the engine driving the most consequential year-to-year climate variations on Earth. To see how it works, we have to establish the ocean's baseline. Normally, strong trade winds blow along the equator from east to west. These winds physically push sun-warmed surface water toward places like Indonesia and Australia. As that warm water moves west, deep, cold, nutrient-rich water is pulled up to the surface along the coast of South America to replace it. This delicate balance between wind and temperature acts as a master switch. As long as it holds, global weather patterns stay relatively stable. But every few years, the switch flips. During an El Niño phase, those steady trade winds weaken. Without the wind holding it back, the accumulated warm water sloshes back eastward across the Pacific. This movement reshapes the thermocline, the boundary separating warm surface water from the freezing depths. As the warm water surges east, it presses down on the thermocline, flattening it out and choking off the supply of cold, upwelling water along the South American coast. Then there's the opposite extreme, La Niña. Here, the trade winds kick into overdrive. They shove the warm water exceptionally far west, which pulls the thermocline incredibly steep and supercools the eastern Pacific. Because these massive underwater shifts develop months before the atmospheric effects reach land, tracking them provides a vital lead time for global disaster preparation. To monitor these shifts, meteorologists rely on the ENSO observing system. It is a massive network of moored buoys, drifting sensors, and ships constantly measuring surface temperatures and currents in real time. All of that hardware is focused on one specific patch of water. It's a precise coordinate box right on the equator, known as the Niño 3.4 region. By tracking the average sea surface temperature inside this box over a running 3-month period, scientists compare current conditions against a 30-year historical baseline. The resulting number is called the Oceanic Niño Index. This chart tracks that index over the last 2 decades. The rule is mathematical. If the 3-month average climbs half a degree Celsius above the baseline, we enter El Niño. If it drops half a degree below, we have a La Niña. This mathematical trigger gives meteorologists the baseline data they need to build probabilistic forecasts for the coming months. The link between ocean temperature and global weather is driven by teleconnections. When vast pools of tropical ocean water warm up or cool down, they change the air pressure sitting directly above them. That pressure shift ripples upward, redirecting the high-altitude winds that steer our weather. This map shows the typical wintertime pattern during El Niño. The Pacific jet stream shifts south toward the equator and gains strength. For North America, this usually brings storminess and heavy rain across the southern United States, while the northern states stay unusually mild. This map illustrates La Niña. The jet stream gets pushed northward into a rigid wave pattern. Now, the northern states take the brunt of the cold and storms, while the south dries out. This phase also reduces vertical wind shear in the tropics, creating an environment for Atlantic hurricanes to strengthen. Outside of North America, the effects are severe. The same shifted winds that cause a dry winter in Texas can cause catastrophic droughts in South America or decimate the Indian summer monsoon. These phases act as atmospheric blueprints, connecting localized ocean shifts to a predictable sequence of seasonal weather patterns worldwide. For centuries, paleoclimate records show ENSO operated on a relatively stable rhythm. Starting around the 1950s, that rhythm began to rupture, giving way to stronger and more volatile swings. The complication is greenhouse warming. The eastern equatorial Pacific is heating up at a faster background rate. This heat increases upper ocean stratification. The ocean separates into distinct layers, creating a rigid physical barrier between the warm surface and the cold deep water. This intense layering alters how the ocean moves. It changes the way the wind pushes the water and how the thermocline tilts, rewriting the physical rules that govern the Pacific engine. This chart tracks the thermocline slope index over recent years. The erratic downward spikes reveal the scientific projection of this stratification. Sea surface temperature variability is increasing. The extreme highs of El Niño and the severe lows of La Niña will happen more frequently. Because the ocean dynamics are changing, the atmospheric teleconnections are shifting too. Models project these weather disruptions will intensify and move further eastward, impacting rainfall and storm patterns over North and South America. Even with improved data, forecasting exactly when and where storms will hit isn't a guarantee. The atmosphere has its own chaotic internal fluctuations that happen independently of ENSO, which means seasonal forecasts will always deal in probabilities. We are watching a natural cycle on steroids. As global warming pushes the entire system into uncharted territory, historical averages aren't enough anymore. Tracking these real-time oceanic shifts is our most reliable guide to surviving tomorrow's climate extremes.